full wave rectification. So actually in full wave rectification you will find that now the current flows through the load for both half cycles of the input AC voltage. So I can say that for full wave rectification, current flows through the load for both half cycles of the input AC voltage. So you'll find that throughout the cycle, current will be flowing through the load. Now, we have two types of full wave. So, types of full wave rectification or rectifier. Types of full wave rectifiers. So the first one we say center tap circuit. Center tap circuit, or sometimes we call it the biphase. Call it the biphase rectifier. Then number two, we have the bridge circuit rectifier. Bridge circuit rectifier. So we shall start by looking at the center tap or the biphase. So biphase half wave. So we call it the biphase rectifier. So we'll have the circuit diagram and the waveforms. So that is our circuit diagram for the biphase half wave. Now you'll realize that it uses a center tapped transformer whereby now you can see the secondary voltage is divided into two voltages, V1 and V2, whereby the two voltages, they are equal but 180 degrees out of phase. Then we have two diodes. So what happens here is very simple. You find that current will be flowing through the load for both the cycles of our input here. So what happens during the positive half cycle, when now our point A here is positive with respect to our center tap point here, which we can name point E, the diode D1 will be forward biased and the current will flow through the load through the path A, B, F, E and back. So you can see this current flows through the load, that is during the positive half cycle. Secondly, during the negative half cycle, the point D will be positive with respect to our center tap point E. Now the diode D2 will be forward biased, and you can see the current will be flowing through the load along the path D, C, F, E. So you can see the two currents, they are all in one direction. So the waveforms, this is the waveform of our input, whereby the two voltages V1, you can see it, and as I said, the two voltages are equal but 180 degrees out of phase with each other. So you find that for the output waveform, there is flow of current throughout. That's why the waveform appears like so, unlike the single phase half wave rectifier, where current was only flowing through the load during the positive half cycle only. So we can also do the analysis here and find the parameters. So analysis, maybe we can start from this point. Analysis. So we can get the VDC. So the first one here is the VDC. So now you see it is the same secondary voltage that was split into two. So now we are going to split the 2 pi, so it is 1 all over pi, the integral from 0 to pi, Vm sine theta. Vm sine theta, this is our input, Vm sine theta with respect to theta. So whereby this will give us, maybe we can have Vm all over pi into negative cos theta from 0 to pi. If you simplify this, you get 2Vm all over pi. So you will notice that now our voltage is twice the single phase half wave rectifier. Yeah. Because this 2 over pi, you can write it as 0.636 Vm is allowed. So the same way you can get IDC if you want the DC current. IDC will be equals to VDC all over RF plus RL. So VDC is here. 2 Vm all over pi into Rf plus Rl. So that will give you the IDC. So we can also get the root mean square voltage. Root mean square voltage. So the second one is the root mean square voltage, V RMS, which will be the square root 1 all over pi. The integral from 0 to pi, we square our input, Vm sine theta squared d theta. So be a step here. So we shall have Vm squared all over pi. So into the integral from 0 to pi, a half into 1 minus cos 2 theta. So on simplifying this, we shall get Vm all over root 2. Vm all over root 2. That one will be our VRMS. So the same, we can get IRMS. IRMS will be our VRMS divided by total resistance, that is Rf plus Rl. So this is going to be Vm all over root 2 into Rf plus Rl. So again, we can get another parameter, that is the form factor. Form factor, Roman 3. Form factor is denoted by FF. It's normally given by the VRMS all over VDC. VRMS all over VDC. So we have our VRMS, Vm all over root 2 divided by VDC 2Vm all over pi, 2Vm all over pi, which if you simplify, it will give you pi all over 2 into root 2. 2 into root 2. Then now we know if we have the form factor, we can get what we call the ripple factor. So ripple factor, you know, it is the square root of the form factor squared. So form factor squared minus 1 will give you the ripple factor. Then we can get another parameter, that is the rectification efficiency. So rectification efficiency which is presented by that symbol, will be given by VDC all over V RMS squared times 1 over 1 plus RF all over RL. This will give us the rectification efficiency. So if we insert them, we know what VDC is. So 2 Vm over pi, 2 Vm all over pi over Vm all over root 2. So squared times 1 all over 1 plus RF all over RL. This gives us all this. We have 0.812 all over 1 plus RF all over RL times 100, which is 81.2%. That is if RF is very much smaller compared to RL. So you can see the efficiency for this particular circuit. So meaning the more we have the number of phases, the efficiency improves. So the peak inverse, PIB, is normally these two voltages, our V1 plus V2, so which are our VM, so VM plus VM, which is normally given by 2 VM. So peak inverse voltage is normally 2 VM. So that's all about the center tap or the biphase. Can also look at some 2 questions on this. So the first example here, actually if you're told to compare the biphase and the single phase half wave, you can see we have a better efficiency, and also the ripples, the ripple factor. We have low ripple factor, meaning we don't have so many ripples in our output. Then the form factor is also low. So the first example number 1, calculate the VDC and voltage regulation. For the circuit below. So that is our circuit. So it is just similar to our previous circuit, that is the biphase. It's only that now the load has been suspended down here instead of having the load in between the two diodes. It is still the same position. So to get the VDC, actually our VDC here is the voltage across the load. So for biphase, you know that VDC is given by 2Vm over pi. So 2Vm all over pi. So now, maybe if you are given the forward resistance of the diode, you subtract it. So that is VD. VD. That is the diode voltage. So, but Vm, because we don't have, we can get the Vm. Vm is given by root 2 times our RMS voltage, which is the secondary. So root 2 times 9. And this gives you, okay, can use that expression. Then now we can substitute for this Vm here to get the VDC. So therefore our VDC will be 2 times root 2 times 9 all over pi times 9 all over pi. We subtract the diode voltage, which we consider silicon, so we subtract 0.7. Subtract 0.7, it gives us 7.4 volts. 7.4 volts. So that is the voltage across the load. Now, to get the no load voltage, we shall get the VDC assuming that there is no voltage drop across the diode junction. So now for VDC no load, now we talk of VDC no load. So VDC no load will be 2 root 2 times 9 all over pi. So for no load, we assume no drop across the diode. For our case, this gives you 8.1 volts. 8.1 volts. So regulation, which we know is given by V no load minus V full load FL over V FL 8.1 minus 7.4 all over 7.4 times 100. This gives a regulation of 9.46%. That is the solution for that question. Maybe the last question here, or the last example, the questions are many, so maybe the last example for the biphase. Yes. A biphase rectifier. Biphase rectifier supplies an inductive load. Supplies an inductive load from a 240 volts, a 240 volts single phase supply. Now the load current is level at the load current is level at, meaning that's the maximum value, at 12 amperes, and the mean load voltage and the mean load voltage is 150 volts. Is 150 volts. So assuming each diode to have a volt drop of 0.7 volts, determine then Roman 1 peak secondary voltage Kva rating of the secondary winding and lastly peak reverse voltage rating of each diode. So we look at the solution. So the solution. So Roman 1, we can have the expression of our VDC, which is the mean. I said the mean is the same as the VDC, V mean, so that it is given by 2 times the maximum, Vm or Vmax, all over pi. Then we subtract the diode rating. So from there, we can now find the Vmax. So Vmax will be given by pi over 2. So we make this Vmax the subject. Pi over 2 into 150, because V mean was given as 150 volts. So 150 plus, because this diode rating 0.7 goes to the other side, plus 0.7, it gives us the Vmax as 236.72 volts. So now RMS voltage across each half of secondary, because we saw that the secondary voltage is divided into two. So from 1 to RMS voltage across each half of secondary winding. Actually, this is our V max all over root 2. That is the RMS voltage over root 2, which will be V max 236.72 all over root 2. This gives 167.4 volts. 0.4 volts. Then now RMS current in each half. So RMS current in each half of secondary, in each half of secondary winding will also be I max all over root 2, because we said the voltage waveform and the current waveform, they are similar. So now the same expression for the RMS voltage here is the same expression for the IMS. But I max was given because we are told that our current, it had settled at a figure here, which is 12 amperes. That was the level. So the phase supply. So the load current is level at 12 amperes. So that is our I max. So this will be 12 divided by root 2, which gives 8.485 volts. No, this is current, which is amperes. So now we can get the Kva rating. Kva rating. So therefore, Kva rating of secondary winding will be 2 times 8.48, 2 times 8.48. Actually, this should be 12. Just a minute, calculator. So this will be 2 times 8.485 times 16 or 167. 167 point, our 167 is here, 0.4. So we are multiplying by 2 to get the rating of the secondary, because you remember we had 2 voltages, because the secondary, since we are using a center tapped, so we have 2 voltages that are out of phase. So this gives 2.84 2.84 kVA. And now we can get the peak inverse of each diode. 13, peak inverse voltage of each diode will be equals to 2 times Vmax, which is 2 times 236.72, which is 473.44 volts. That's all about that question. So thank you so much for listening. So for today, so our next lesson will be on bridge rectifier as well as three-phase rectifier. So we shall look at the three-phase, and of course, if there will be time, we shall go to the control rectifiers where we use thyristors. So for more questions, there are more questions that can be used for practice.